Hello! In this video, we are going to prove the following theorem. Let m and n be integers, where m is less than or equal to n. Then, for all lists of real numbers am through an and bm through bn, if 1, ai is less than or equal to bi for all integers I between m and n, and aj is strictly less than bj for some integer j between m and n, then the sum from I equals m to n of ai is strictly less than the sum from I equals m to n of bi. Okay, now in proving this theorem, we are going to rely on the following fact. Given integers m and n, where m is less than or equal to n, we have that for all listed real numbers am through an and bm through bn, if ai is less than or equal to bi for all integers I between m and n, then the sum from I equals m to n of ai is less than or equal to the sum from I equals m to n of bi. Okay, now let's get into proving this theorem. To start on the proof, let's give ourselves an integer n. And from here, we're going to proceed by induction on n to show that for all integers n greater than or equal to m, that this is true. So let's start with the base case. In the base case, we're trying to prove that this is true in the case where n is equal to m. Which means we're trying to prove that for all listed real numbers an and bn, if both 1 and 2 are true in the case where n is equal to m, then this is true in the case where n is equal to m. Okay, so to start out, let's give ourselves two lists of real numbers an and bn. And from here, we want to show that if this is true in the case where n is equal to m, then this is true in the case where n is equal to m. So let's suppose that both 1 and 2 are true in the case where n is equal to m. Our whole goal from here is to show that this is true in the case where n is equal to m. Well, since j is both greater than or equal to m and less than or equal to m, these two inequalities together tell us that j must be equal to m. So since j is equal to m, am is less than bm. And now let's show that this is true in the case where n is equal to m. To start, let me write this sum in the case where n is equal to m. Now, since the lower and upper bound of the sum are the same, we know that this is just going to be an. And we know that am is strictly less than bm. But in a similar way to what we have here, we know that bm is just the sum from I equals n to m of bi. So as you can see, this is strictly less than this. In other words, we have shown that this is true in the case where n is equal to n. And that was our whole goal, so this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to m, where this is true. The whole goal of the induction step now is to prove that this is also true for n plus 1. So really, we're trying to prove that for all lists of real numbers an through an plus 1 and bn through bn plus 1, if both 1 and 2 are true in the case of n plus 1, then this is true in the case of n plus 1. So let's start out by giving ourselves two lists of real numbers an through an plus 1 and bn through bn plus 1. From here, we want to prove that if this is true in the case of n plus 1, then this is true in the case of n plus 1. So let's suppose that both 1 and 2 are true in the case of n plus 1. Our whole goal from here is to show that this is also true in the case of n plus 1. Now to start, it's going to be useful to know that since this is true for all I between m and n plus 1, well then clearly this is also true for all I between m and n. Now from here, we are going to break this up into two cases. Either j is equal to n plus 1, or j is strictly less than n plus 1. In either case, we are going to prove that this is true, where we have n plus 1 here. So let's start with case 1, where j is equal to n plus 1. So I'll start out by writing the sum that we have here, where we replace n with n plus 1. Now since n plus 1 is strictly greater than m, we can pull away the n plus 1th term from the sum, so that we get the sum from I equals m to n of ai plus an plus 1. Now, remember from what we have above that ai is less than or equal to bi for all I between m and n. So we can use the fact that we have right here. If we consider the lists am through an and bm through bn, well, we know that if this is true, then this is true. But we know that this is true, that's what we have right here. Therefore, this must be true. So the sum from I equals m to n of ai is less than or equal to the sum from I equals m to n of bi. Which means this must be less than or equal to this. But now, since j is equal to n plus 1, this means that an plus 1 is less than bn plus 1. Which means that this must be less than this. But then, we know that adding these two together gives us the sum from I equals m to n plus 1 of bi. So as you can see, this is strictly less than this. Which means we have shown that this is true, where instead of n, we have n plus 1. And that's exactly what we wanted to show. So this completes case 1. Now let's move on to case 2, where j is strictly less than n plus 1. Now, in this case, we are going to apply our induction hypothesis, which is this statement right here. And to use our induction hypothesis, we are going to take these two lists to be this list and this list. And from here, we want to show that both 1 and 2 hold. Because if we can show both 1 and 2 hold, by our induction hypothesis, we will be able to conclude that this is true. Well, we already know that 1 holds, because that's what we noted right here. So all that's left is to show that 2 holds. Well, since we're dealing with integers, we know that this is equivalent to saying that j is less than or equal to n. And of course, j is greater than or equal to n. And so what this means is, we have that aj is less than bj for some integer j between m and n, which is precisely what 2 says, so 2 holds. So since both 1 and 2 hold, we have by our induction hypothesis that this must be true. And now, let's show that this is true where we have n plus 1 here. And we'll start out by writing the left-hand side. Now, we know that this is the same thing as the sum from I equals m to n of ai plus an plus 1. And then, because of what we have here, this must be strictly less than this. And then, because ai is less than or equal to bi for all I between m and n plus 1, well then surely an plus 1 is less than or equal to bn plus 1. And because of that, this must be less than or equal to this. And we know that this is equal to the sum from I equals m to n plus 1 of bi. So as you can see, we have shown that this is strictly less than this. In other words, we have shown that this is true where we have n plus 1 here. So putting this together, we have that in either case, this is true where we have n plus 1 here. And so this means that we have shown that this statement is true for n plus 1. And that was the whole goal of the induction step, so this completes the induction step. And because we've done both the base case and the induction step, this closes the induction. Which means we have shown that for all integers n greater than or equal to m, this is true. So, really, given any two integers m and n, where n is greater than or equal to m, this is true. So we have proven exactly what we wanted to prove. So this completes the proof. And so yeah, that's pretty much it for this video.